Chapter 7, Section 1, Day 1 starts talking about exponential models. Exponential models are repeated multiplication, which means things get really big really fast. So if you take a look at the first section, they want you to learn how to graph an exponential function. So letter A, y equals 2 to the x. Your best bet at this point is to pick values of x, plug them in, and get values of y back out. Typically speaking, when we do that, we like to pick 3 values, a negative, 0, and a positive. If you put a negative in to the negative 1 is in the air, gives you 1/2. Negative 1/2 is right there. Oh, just kidding. Up further. Sorry about that. If you put a 0 in, 2 to the 0 is 1. And if you put a 1 in, 2 to the 1 is 2. So you're going to notice these exponential functions hug the x-axis as close as you can, and then they go up very quickly. So generally speaking, that's what they look like. Letter B, y equals 4 to the x. Again, I'm going to choose a -1, a 0, and a 1. If I put a -1 in, 4 to the negative first is 1/4. I'm trying my very best, but the pen tip is a lot larger than the graph. If I put a 0 in, 4 to the 0 is 1. And if I put a 1 in, 4 to the first is 4. So this one's a little different than the one we just did because it gets bigger faster. So if you notice, the right-hand side of that graph gets a lot steeper, a lot faster than letter A. Letter C, y equals 1/3 x. So again, I'm going to choose values of x, plug them in, and get values of y back out. If I put a -1 in, 1/3 to the -1 is 3. 0, if I put a 1/3 to the 0, I get a 1, and 1/3 to the first is 1/3. So -1, 3 is right there, 0, 1, and 1, 1/3. So if you notice, this one's kind of going to go backwards. It's going to start high and end low. And the difference is the fraction. When your base is a fraction, it ends up taking the graph and starting it high and ending low instead. And we'll learn what that's called a little later. Letter D, -1, 0, and 1. Putting a -1 in. 4 to the -1 is 1/4. Times 3/4 is a 3/16. And let the calculator do that for you. If I put a 0 in, 4 to the 0 is 1, times 0.75 is 3/4. And if I put a 1 in, 4 to the first is 4, times 3/4 is 3. So I have a -1, 3/16, that one's really close there. 0, 3/4, and 1, 3. So the difference between this one is actually this 0.75 out front. That 0.75 tends to move my 0, 1, which occurred everywhere else. If you take a look at the tables we have, 0, 1 was a common order pair, but it wasn't 0, 1 in the last one because of the 0.75. The generic general function for exponentials is y equals a times b to the x. The y-intercept is 0a, so just like I talked about that 0.75 changing the 0 ordered pair, that value that's out front will be your y-intercept value. The domain for every exponential function is all reals. From left to right, this graph will go on and on forever. But there's an asymptote at y equals 0, meaning the x-axis. So I'll come back to this in a second. If you look at the x-axis of this graph, the graph hugs it, meaning it never actually touches this x-axis right here. It'll never touch it, and it'll never go below it, because no matter what value I put in for x, I'm never going to get a y value down here. I'm never going to get a negative y value, and that's really important. So that means that this green line I put in here is called an asymptote. The equation is y equals 0. Your function will never go below that. The range is always y is greater than 0 because of that asymptote, meaning that it only touches things above it. There are two kinds of exponential functions. The first is a growth. So I'm looking at the stuff in green right now. A growth means that your b value is greater than 1. Anytime that happens, you're increasing by a constant percentage. It's called a rate of increase or growth rate. And in order to find that v value, you take 1 plus your rate. In a decay, you've got a fraction that's between 0 and 1, and that means it's decreasing. We call that a rate of decay or a decay rate. You usually express it as a negative quantity because it's in fact getting smaller instead of bigger. So if you take a look at example 2, they want you to identify whether it's a growth or a decay, and they want the y-intercept. And again, the growth or decay factor comes from whatever is being raised to x. So if you look at letter A, the value being raised to x is 0.95, and that's between 0 and 1. So this is actually a decay. So in this situation, we're looking at this side right now. It's between 0 and 1. To find the y-intercept, and again, that's right here, the y-intercept is 0a. So this y-intercept is 0.12. Letter B. The 2 right there tells me that this is a growth, and the y-intercept is the a value, so 0.25, or 1/4. In letter C, that 4 is bigger than 1, which means this is also a growth, and the y-intercept will be 0.3. Keep in mind that the y-intercept is where it starts, technically speaking, when time or the independent variable is 0. Letter D, this 0.75x is between 0 and 1, which tells me this is a decay, and the y-intercept is 0.11. Letter E, you put $2,000 into a college savings account for 4 years. The account pays interest. Pays interest means that this account is a growth. What you need to figure out for the y-intercept is where it would start. So when time is 0, where did you start? And that happens to be what you put into the account to start. So this one is 2,000. Be careful with letter G, even though it looks like a fraction, 5/4 is bigger than 1, which makes it a growth. The word depreciates in letter H means it's a decay. Depreciates means to get smaller, to lose value.